a fifth-year PhD student in Youngbaek Kim's group, and today I'm going to be presenting my work on classical dynamics of quantum spin liquids. So I hope you enjoy. Okay, so for the outline of this talk, I'm going to first be presenting a background on quantum spin liquids. What are they? Why do we find them interesting? And then I'll comment on some of the recent progress on Kitaev spin liquids in recent years, and more namely, some of the experimental developments in discovering them. And then I will talk about my piece on all this, which is simulating spin dynamics of Kitaev spin liquids using classical dynamical simulations. Okay, so when you have spins that are localized on a lattice, you can have a couple of different states arise, and one of them is the traditional magnetically ordered state. So these are just when you have spins that are pointing in some direction and they're ordered. In this case, it's a ferromagnetic state, so then they're all pointing in the same direction. And these states break spin rotational symmetry, and so the excitations are magnon excitations. Here I've depicted another type of state known as a quantum spin liquid state. Note that this is Canva AI generated because we haven't actually realized a real quantum spin liquid state confirmed unambiguously in real experiments. So for now, we get the pretty AI generated one. And these states actually evade ordering even down to zero temperature. So in the magnetically ordered state, they might be fluctuating due to some temperature, but then when you go to zero temperature, it orders and it picks a direction. But even down to zero temperature, they're still dynamically fluctuating. And the thing about these states is that they don't break symmetries in this framework of Ginzburg-Landau theory. They do not break symmetries, and so there's no order parameter. And so for quantum spin liquids, okay, cool. We know what they are, but why do we care? Well, these are highly entangled states of matter, which has a few consequences. So first of all, these states can host fractionalized excitations, which can include anyons in 2 dimensions and spin-ons. And if you were in Subir's talk, you can see, well, actually, he didn't mention Majorana fermions, but so anyons have been proposed for use in topological quantum computing, which may be of interest to you guys, this audience. And there also is emergent gauge fields. So you can get, Z2 and U1, which is, classical electrodynamics on a chip on your tabletop, but then you can also realize higher rank U1 in spin liquid states. And so from a fundamental science point of view, it's interesting because you can get field theories beyond the standard model on your tabletop, which is very nice. But then from a quantum technology point of view, you can proposed braiding of these non-abelian anyons. And these would form the qubits for your topological quantum computing states. Okay, so how do you make a quantum spin liquid? One of the main ingredients in actually making these states is frustration. So what is frustration? Frustration is when you have competing interactions that cannot be simultaneously satisfied. So just a classic example, this is an example of geometrical frustration when you have the antiferromagnetic Heisenberg model on a triangular lattice. One spin points up, the other spin wants to point down, but question mark, where does the third spin want to point? Is it up or down? And either of those configurations would give you the same energy. So we don't know which one it wants to pick. However, when you actually simulate this, you actually get a magnetically ordered state, so it's boring. So I won't actually be talking about the triangular lattice. However, there's other types of frustration. So for example, this is known as bond frustration. So each bond on the honeycomb X, Y, and Z has an independent Ising axis. So for example, across the X bond, the spins want to point perpendicular to that bond. Across the Y bond, the spins want to point perpendicular to that bond. And across the Z bond, they want to point perpendicular to that. So if you have all of these spins on a lattice, this middle one is going to be it doesn't know, it has to choose between the three directions. So one of the spins is going to be happy, and it's just going to be chilling, but the other two spins are upset and they're frustrated. And you can imagine that if you increase the system size, then you're going to exponentially increase the number of degenerate states, the number of equal energy states that forms this manifold. And so, all right, let's cook up a quantum spin liquid. Ingredients. Number one is frustration, which leads to a classically degenerate manifold of equal energy states, which is the process that I mentioned earlier. So how do you make it quantum? You superimpose all of them. So it's a quantum spin liquid is a superposition of all of these classical degenerate manifold of equal energy states. And that's actually the difference between a classical spin liquid and a quantum spin liquid. So when you have a classical spin liquid, then if you, for example, simulate this model at high temperatures and then you lower down to 0 temperature, then it would pick one of these degenerate configurations. But for the quantum spin liquid state, when you go from high temperature to 0 temperature, it's still in this, it's just described by this one wave function. It's not going to collapse into any of those states. And it's in fact still fluctuating even down at 0 temperature. Okay, great. So quantum spin liquids, they're cool, great. How do we actually measure them and detect them in real materials? Unfortunately, there's no order parameter because it's not described by Landau theory. And there are no direct probes for the fractionalized quasi-particles. And so we have to resort to looking for characteristic signatures in many different measurements and kind of combine them together and make a story so that we can form a more complete picture. And that's the only way that I know how to detect a quantum spin liquid. So in this talk, I'm going to be mostly focusing on the inelastic neutron scattering probe. Okay, so let's go to a specific type of spin liquid known as the Kitaev spin liquid. And the Kitaev spin liquid is nice because it's exactly solvable. So for theorists, we can, it's a playground for us to understand and study its properties. It has Majorana-fermion excitations. So actually Kitaev was one of the people that proposed a Kitaev spin liquid state for use in topological quantum computing by adding a field. And so we get these non-abelian anyons. And then to actually, so the model is spin 1/2 on a honeycomb lattice with the bond frustration that I described earlier. And in real materials, there are some candidate materials. One of the leading candidates is this material known as alpha ruthenium trichloride. And it's a 4D material with strong spin orbit coupling, which is important in realizing the Kitaev interaction in real materials. And it's also got edge sharing octahedra. So strong spin orbit coupling and edge sharing octahedra are the ingredients to actually realize this type of interaction in a real material. But surprise, it's not a spin liquid. It's actually magnetically ordered. It's zigzag ordered in its ground state and not a Kitaev, which implies, although it has a strong Kitaev interaction, and you get this bond dependence, it implies the presence of non-Kitaev interactions. And a minimal model for this material is actually described by K gamma gamma prime, where gamma and gamma prime are off diagonal, but also bond dependent interactions. And gamma prime actually stabilizes the zigzag order here. So the question is, can we stabilize a Kitaev spin liquid if we apply a magnetic field? One of the groundbreaking experimental results has measured a half quantized thermal conductivity in alpha ruthenium trichloride. And this half quantization is supposed to be indicative of Majorana fermions. It's supposed to be a smoking gun signature, if you will, of Majorana fermions. And this was done in a finite field, right? And so if this experimental data is confirmed, then do we actually have a field-induced chiral spin liquid? And this is very exciting. However, there's been some controversy in the field because there's been some disagreements among experimentalists. Some people see this half quantization. Some people can't see the half quantization at all. It's, it can't be reproduced by certain groups. So there's lots of discourse. in the field about this material right now. So one group measures actually no half quantization, but they see a strong temperature dependence, which is actually indicative and more consistent with the topological magnon picture, meaning that the underlying order might be actually magnetically ordered instead. Okay, so at zero temperature for the Kitaev spin liquid, here's the phase diagram. At zero temperature, we expect that the Kitaev spin liquid state is stable for a finite region at zero temperature phase diagram. And then there's a phase transition at finite field to a forced ferromagnet state where all of the spins polarize towards the field direction. However, experiments are actually done at finite temperature. And at finite temperature, Majorana fermions are not well defined, first of all. So analytically, it's hard to describe them. And second of all, magnons near this crossover regime, because we're at finite temperature now, it's a crossover from the quantum spin liquid to ferromagnetic state. The magnon description near this crossover is actually very also not well defined. It breaks down with non-interacting magnons. And analytically, it's really hard to write down equations to study this regime and to study both, a coexistence perhaps of the Majorana fermion and magnon excitations. So that's what numerics comes in. And that's the goal of my project here, is to identify the contributions to the thermal Hall effect by studying the dynamics in the crossover region. So I do this using classical Monte Carlo methods. Now you might be wondering, wait a minute, quantum spin liquid, classical simulation methods, how do you do that? That doesn't make sense. And I hope over the course of this talk to convince you that my method is actually valid. And another reason why we use classical Monte Carlo methods is because simulations on the quantum model are notoriously hard. The Hilbert space grows infinitely, and so you get very bad finite size effects when you try to use ED and DMRG. And with some of the regimes that we're interested in, the sign problem also becomes very bad with QMC. And so for now, we resort to classical Monte Carlo methods. And the algorithm goes like this. So first we do finite temperature simulations with Monte Carlo, where we generate an ensemble of spin configurations. And then we take all of these configurations and time evolve them using the Landau-Lifshitz equations of motion, so given here, and we solve for the time dependence of the spins. And from here, we can compute observables such as the dynamical spin structure factor, which is exactly the quantity that you measure in neutron scattering measurements. And furthermore, we can also, from finite temperature Monte Carlo, get information about the specific heat and magnetization of the system. So in this project titled Spin Excitation Continuum to Magnon Crossover, I study this crossover from the supposed Majorana fermion regime and the polarized regime, and I do so in 3 different models with large Kitaev interactions. And I calculate the dynamical spin structure factor, and then I use this to comment on the breakdown of the magnon thermal Hall conductivity. So first of all, what would you expect to see in neutron scattering from the pure Kitaev model? At zero temperature, which is exact, we would see a spin excitation continuum associated with the Majorana fermion excitations. And then at finite temperature, using exact QMC methods, we can, the spin excitation continuum persists. And then as you go to high fields, in both finite temperature and zero temperature, you would see sharp magnon bands or well-defined magnon bands, which are the excitations of the polarized state. And the region we want to study is in between here, where the quantum methods don't work. And by quantum methods, I mean simulations on the quantum model, not quantum algorithms. I know that there is confusion with quantum information people when I've said that before. So, okay. So here are my results for the ferromagnetic Kitaev model. So first of all, we see that it qualitatively agrees with QMC results where there isn't a sign problem, which is quite remarkable because even though we only have classical spins, we're still able to capture the excitation continuum using only classical dynamics. So this is quite surprising and quite amazing. So as you increase the field, you see the definition of the magnon bands starting to appear. And with this, you can define three different regimes, the spin excitation continuum regime, the crossover regime where there's a coexistence between a continuum and weakly dispersing magnon bands, and then the polarized regime. Okay, with this, it kind of gives us permission to look at models where QMC doesn't have any results for, and that is the AFM Kitaev model. So similarly, we can define three different regimes: the spin excitation continuum regime, the crossover regime, and also a polarized regime. And I want to draw attention to this spin excitation continuum regime, because we see as you increase the field, a shift in the qualitative, a qualitative shift in the spectral weight as you increase the field. And there's been some ED calculations on the AFM Kitaev model where they attribute, or they see when they calculate the density of states, a shift in the density of states when they transition between a Kitaev spin liquid and what they call a gapless U1 spin liquid phase. And so we attribute this behavior to actually a crossover between a chiral spin liquid and U1 gapless spin liquid phase. And we're able to capture this using only classical dynamics. Okay, so let's move on to the K gamma gamma prime model, which is the minimal model for alpha ruthenium trichloride. So at zero field, it's got magnon bands associated with the zigzag order, which is what you would expect. And then at finite field, we see large unit cell magnetic orders, which was predicted in the zero temperature classical phase diagram. But at finite temperature, you see that these magnon bands that would usually be associated with magnetic order, they kind of start to blur together because these unit cells are so large. And the size of your unit cell corresponds to the number of magnon bands that you should see. So when you have large unit cell orders, then they kind of just look all blurry together. And we actually see something that resembles a excitation continuum. And this is supposed to be an ensemble of large unit cell orders in the classical case, but in the quantum model, would this actually correspond to a field-induced spin liquid? So that's still an open question to be done. And so I hope this inspires people working on the quantum model to investigate this, even though it's hard. And then we see the spins polarize at very high field, which is what is expected. Okay, so now that we've looked at the dynamical spin structure factor in these, and we've identified these three different regimes, the spin excitation regime, the crossover regime, and the polarized regime, we can comment on the breakdown and validity of the magnon thermal Hall effect when computed using non-interacting magnons. So in the crossover regime, where the linear spin wave theory and the LLG dynamics don't match, then we see a very sharp spike in the magnon thermal Hall conductivity, which may be unphysical. And these are to be taken with a grain of salt because these linear spin wave theory and LLG equations not matching is indicative of the presence of nonlinear or magnon-magnon interactions that may heavily renormalize this peak if you took that into account. And of course, in the polarized regime where linear spin wave theory and LLG matches, then the magnon thermal Hall conductivity is a good description of the transport. So in summary, our FM Kitaev results agree well with unbiased QMC simulations. We're able to capture the crossover behavior from two different quantum spin liquid regimes in the AFM Kitaev model. We observe a continuum in the K gamma gamma prime model, and we're able to identify crossover regimes in all three models and use this to comment on the limitations of the thermal Hall conductivity computed from non-interacting magnons. And we did all of this using Landau-Lifshitz-Gilbert dynamics. And even though it's classical, it's unbiased. We can go to large system sizes and long times. And it includes all higher order magnon interactions. So you don't actually have to assume a quasi-particle picture. We just simulate it, and then it gives us the dynamics. And we're able to, using this technique, capture the key qualitative features that have been seen in many simulations on the quantum model. Okay, that's it. Thank you.